now that you've put together your robot, complete with the light sensor and both servo motors, you'll need to move on to actually programming your robot. In order to do this next portion of your homework, you'll need your completed robot, a USB cable, and then also a small instrumentation screwdriver. These screwdrivers are available in the Phys for you to use. Now that we're all set up, let's go ahead and start using the MPIDE program, which you installed in class during week 2 on your computers. Alright, so you're going to use code that's already been prepared for you in order to complete this homework. You'll log into Blackboard and then scroll down to the weeks 5 and 6 portion of Blackboard. Click in here and then go into reference materials. So once we're in reference materials, we'll select the practice programs folder. From the practice programs folder, we'll select this code called basic time motion. I'm just going to collapse this left sidebar so we have a little bit more room to see what we're doing. Here are some instructions that you'll use to help you complete this task in class. We're going to get familiar with the code first as part of your homework. You'll copy everything from below the equal signs. So we'll drag all the way down. To copy, once you've highlighted everything, in a Mac, you'll press Command-C, and on a PC, you'll press Control-C. We'll click over here in our already opened MPIDE window, and on a Mac, we'll press Command-V in order to paste everything, and on a Windows machine, you'll press Control-V. You can see the code is pretty small to read, so one of the first things we're going to do is go up to MPIDE and Preferences. On a PC machine, you'll get to this option by going to Window and then Preferences. Here we can see the font size. We'll increase this to 14 so that we can easily read the code. You'll notice that the colors have changed as well as we moved from the code in Blackboard to the code in MPIDE. These colors show us that these particular words have special function or special meaning to the MPIDE code. Let's go ahead and take a look at the flowchart that corresponds to this set of code. So part of good programming practice is always to put together a flowchart so you can help organize your thoughts before you begin to write any code. Since we've given you the code already in Blackboard, we're going to spend a little bit of time talking about how the flowchart corresponds to the code. We have 3 sections inside the code. One where we have global variables that we define at the very top of the code. Here we're going to include a servo library, which is a collection of code that we can use without having to write it. And we're also going to declare the left and right servo motors. Then we'll move into the second or the middle portion of the code, which is the setup function, highlighted in blue here. Within the setup function, we're going to attach the left and right servo motors, set up communication to the serial monitor, set both servo motors to go forward at 100 speed, and then we're going to set a delay to keep the servo motors continuing to go forward at 100% speed for 1 second. And then we'll stop both servo motors. Finally, at the end of the program, we will include the loop function. All 3 of these must be present in the code for the MPIDE code to run. However, in this program, we're not going to actually execute any commands in the loop function. So instead, we'll just use a comment as a placeholder within the loop function. Alright, so now that we've copied over the code and changed the font size so we can read it, let's take a minute and look at how the code that we have corresponds to a flowchart. Flowchart is commonly used in programming to help you organize your ideas before you actually start to write any code. So then you're writing code in a more efficient manner. Our flowchart and our program itself can be broken down into 3 separate sections. And we're going to focus only on the parts of the code that are above this green fence with user-defined functions. Anything that's below this fence, things that you don't need to worry about. It's code that your instructors and peer mentors have already written that will just work for you out of the box. Within the code, there are 3 separate sections that we're going to work with. These first 2 lines here, where we include the servo library and we declare the left and right servo motors, are known as global variables. And those are these 3 lines of code here, where we include the servo header file, which is a library or a collection of other code that we don't need to write. And we also attach the 2 servo motors. Then we come to the middle section of our code, which is the large setup function, everything that's outlined in blue here. Within this code, we're going to attach the left and right servo motors, here and here. Then we'll set up communication to the serial monitor with this line serial.begin 9600. 9600 is the baud rate, or the speed at which our microcontroller will talk to the computer. Then we'll start the driving process by telling both of our servo motors to go forward at 100% speed. We're going to use these two functions, right forward and left forward, in order to tell the microcontroller to drive the robot forward. And we're going to continue to have the robot, or the microcontroller, drive the robot forward at 100% speed for 1 second by using this function right here, which says delay 1000. The delay function takes arguments or inputs in milliseconds. So we need to write 1000 in order to get 1 second of time, because there are 1000 milliseconds in 1 second. Finally, within the setup function, we'll stop both of the servo motors. With these commands, right forward, 0% power, and left forward, we're going to change this 100% power to 0% power, which will have both of the servo motors stop. Finally, the last portion of the code that we're going to work with is the loop function. Within the loop function here, we're not actually executing any commands, but MPID requires that we have these global variables, the setup function, and the loop function within the code in order to run. So we're using a comment, which is green, with these 2 forward slashes, as a placeholder for the loop function. So now that we've talked through our flowchart, we're going to upload the code from Basic Time Motion that we took from Blackboard onto our microcontroller. Before we do that, we need to check to make sure that we're using the right microcontroller and that we're using the right serial port, or the USB cable, to talk to our microcontroller. So we'll go up to Tools, both on a Mac or on a PC. First we'll go to Board. We'll go down to Chip Kit, and you'll want to select UC32 by clicking on it here. That's the first thing we need to do. Second is to check the serial port. So we'll go back to Tools again, go to Serial Port, and then on both PC and a Mac, want to make sure that we're using the USB serial command. On a Mac in particular, you want to make sure that you use the tty.usb serial command. So we'll click on it to confirm that that's our choice. Alright, so now that we're ready to upload this code to our robot, we're going to connect the robot to the computer with the USB cable. When we've pressed it in enough, we'll notice that the lights flash. This red power indicator indicates that there is power going to the microcontroller. Set this down, and now take a look at our code. Have the code from Blackboard, and we'll push Verify first, which is the play button. That will compile the sketch. We'll look for the message right here that says Done Compiling. That lets us know that the verification was successful. Now we'll go up to this button, it looks like Fast Forward, which is the Upload button, and we'll upload it. Before we press Upload, we want to make sure that our robot is on a flat, level surface. Now we'll press Upload, and again we'll look at the gray status bar, see when it is done uploading. And it's thinking about it as it uploads. You can see the red lights flashing, and then our robot drives forward for 1 second, and as you can see, it continues to drive forward even though we've told it to stop. This is because the servo motors are not calibrated, so our next step is to calibrate the servo motors. So now we're going to use our instrumentation screwdriver to adjust the potentiometer inside each of the servo motors. If, when you assembled your robot, made it so that these yellow screws were facing towards the tail ball of the robot rather than the light sensor of the robot, now would be a good time to go and reinstall the servo motor so that the yellow screw faces forward. This will make your life much easier when you go to calibrate the robot. We're going to adjust each of these screws, both with the left and the right wheel, until the robot stops spinning the wheels, because now we've told it to stop, but yet the wheels are continuing to spin because it's not calibrated. So first, we'll gently turn the screw counterclockwise. We noticed that the wheel direction changed. So now we'll turn clockwise very, very slowly, probably less than 1/8 of a circle. You can see it's not quite right, so we need to turn it counterclockwise till the wheel stops spinning. And then we'll repeat the process on the next wheel. All right, so now we're going to check our calibration by pushing the reset button, which is right here. The reset button will allow us to run the last program that was loaded onto the microcontroller without needing to reinstall or re-upload the code. For Mac users, if you're having trouble with an AVR-dude timeout error, you can also push and hold the reset button while you're uploading the code to your UC32 microcontroller. This will help you to complete the upload of your MPIDE code. We'll go ahead and push the reset button, again right here on the edge of the microcontroller, to see if our robot drives forward for 1 second and then stops. All right, so this affirms our servo calibration is complete. All right, so now we're going to move forward with adding some lines of code into the existing basic time motion code that we pulled from Blackboard. We're going to add in 2 print statements that will allow us to display messages from our microcontroller to the serial monitor on our computer. So we've added these 2 messages into our flowchart. They're this right here, print out let's drive for 2 seconds to the serial monitor, and then also this box right here, which will have us print out stop and hold. Notice that both of these boxes are after we set up communication to the serial monitor. It's important to make sure that we have this line to set up communication to the serial monitor, the serial.begin 9600, first, so that we tell our UC32 microcontroller that it is talking to the computer at this 9600 baud rate. So let's go ahead and type these lines of code into our microcontroller. And you'll do this on your own computer as part of your homework. We'll add a new line after the serial monitor by hitting return a couple of times. And then we'll indent by 4 spaces so that we keep the code nice and easy to read. The command that we're going to use to print out a line and then hit enter after that line is serial.println. We need to capitalize serial. Notice that it turns purple. So I'm going to do println. Notice how println turns orange. So it's a key word. Now we'll open with an open parenthesis, add a double quote. We'll type let's drive for, and we're going to go for just 1 second. Notice how once we add the second quote, the entire string turns blue. This means the microcontroller will print out exactly what is shown in blue to the serial monitor. All right, so that is this box right here. Now we'll go ahead and add the printout stop and hold line after the delay. So here's our delay function, and here are our stop commands. So we want to add in the serial.println line here, in between those 2 commands. So we'll click here, hit enter a couple of times, whoop 1, 4 spaces in to make it easy to read, capitalize serial, print, oh, gotta spell print correctly, ln, so that it changes orange, open parenthesis, double quote, stop and hold. Notice again, once we add the close double quote, the line turns blue, close parenthesis, and then a semicolon. We always want to make sure that we end the code in a semicolon. This acts as a period for our MPIDE program. It tells the microcontroller when we've reached the end of a line. Now that we've added these 2 lines in, we'll go ahead and first verify the code to see if we've made any mistakes. You can see here we have an error message where it says error running when we tried to verify the code. When we read in the code, we can see that it tells us that the error is in function setup, which tells us that that error is before this closed curly brace, after this open curly brace, because these two curly braces define the extent of the setup function. They're similar to the blue box that we used over on our flow chart. So we'll look for our error in between these lines here. The second line in our error message says it expects a semicolon before write forward. So we'll look at our first write forward from the bottom, and we'll look at the line before it that we added. Notice we've got a semicolon here, so the error message isn't talking about this line. Let's go up to the first time where we use write forward command, and we'll look at the line before it. Notice here, we forgot to put a semicolon when we type this code in, so we need to add a semicolon at the end of the line. We'll check now to see if this was the correct error by going up to verify the code again. See how it tells us here, done compiling with a binary sketch size of some bytes? When you see this message that says binary sketch size, that means that you've successfully verified your code and that the code does not include any programming, spelling, or typo errors. There are a number of different errors that you can accidentally make while you're coding. There's a sheet on Blackboard under the weeks 5 and 6 reference materials folder to help you find and avoid some of these errors. So you go to Quick Reference Guide. This is a PDF that will show you all of the different errors that you may run into when you are coding. Alright, so now that we've ensured that the code is correct, because we've got the done compiling message, we'll go ahead and upload the code to our UC32. Remember, we're going to use the upload button, and on Macs, you may need to push the reset button and hold it in order to successfully upload the code to your microcontroller. Push the upload, and we'll wait for the error message or for the messages to tell us that the upload has been successful. Also note that our microcontroller has flashing red LEDs. This tells us that the microcontroller is communicating with the robot. And we saw that the robot moved forward for 1 second, but we weren't able to see any of the messages which we coded because we didn't have the serial monitor open. So let's go back and open up the serial monitor on our computer. Alright, so this icon right here stands for the serial monitor. Remember when we were calibrating our servo motors, how we were able to press the reset button and it ran the code that was already on the UC32 without us needing to upload the code? The serial monitor will do the same thing. So as soon as I click on this button, we'll see our robot drive forward for 1 second again. So here's our serial monitor. And we can see here that the robot did indeed drive forward for 1 second and print it out. Let's drive for 1 second. And then it returned. On a new line, we have stop and hold, and the robot is continuing to stop. The last part of your homework will be to explore how the loop function works. We saw how the setup function executed all of the commands within the blue outline and then stopped, didn't continue. The loop function does something different. It executes all the commands in between the open and the closed parentheses over and over and over again until you disconnect the microcontroller from the computer. We're going to demonstrate this by taking this print statement from the setup function where it was before and placing it into the loop function by itself. So over in our code, we're going to copy and cut this line and paste it down into the loop function. So let's go ahead and do that. We'll highlight the line of code. On Mac, we'll hit Command X. On a PC, that would be Control X. Select this line. Command V to paste, and on a PC, that's going to be Control V. Again, we'll go ahead and verify our code, check to see if we have any errors, like a missing semicolon. So it's done compiling, binary sketch size, so we know that our compile was successful. Let's go ahead now and upload this code to our microcontroller. So we'll push the fast forward, the upload button. Once this is done, we expect it to tell us that it's done uploading, and then we'll see our robot drive forward. But we won't be able to see the messages until we open up the serial monitor again. Okay, so now, again, remember when we open up the serial monitor or when we push the reset button on our microcontroller, this allows us to run the code again without uploading it. So we'll click on this icon, open up the serial monitor. We'll have it run, and we see how it continues to print out stop and hold over and over and over again until we disconnect the USB cable. And then we can see that it stopped mid-sentence when we pulled out the USB cable from the microcontroller. This is because the stop and hold command or print statement is inside our loop function, and it continues to run over and over and over until we disconnect the microcontroller from the computer by removing the USB cord. Alright, so once you've completed this code with your own robot, you will need to save this code with the 2 print statements that we added on your computer, your laptop, and on your UC32 to demonstrate to the TAs in class. You'll also use a flowchart like the ones that we worked with to complete your week 4 notebook entry. And you should also watch the video to walk through the different experiments that we will conduct with the robots in class during week 5. See you in class.